Let's get some practice solving differential equations that have Heaviside functions in them using the Laplace transform. So let's take this example. X double dot plus 4x is equal to the Heaviside function of t minus 5. And the initial conditions x at 0 is 0 and x dot at 0 is 0. So again, that is their Heaviside function there, shifted over to t is equal to 5. And we wanted to solve this using the Laplace transform. Before we do that, let's just think about what this means. So if t is less than 5, for example, then the right-hand side is just 0. And we're stuck with the initial conditions of 0 for x and 0 for x dot. If t is greater than 5, however, then the Heaviside function turns on, and so we have a positive 1 on the right-hand side of our differential equation. And what we're going to do is use the Laplace transform to put both of those pieces of information together. And the beautiful thing about Laplace transform is it does both of them at the same time. And so we don't have to solve the differential equation separately for t less than 5 and t greater than 5. We can just solve the differential equation once using the Laplace transform, and it takes care of everything. So let's remind ourselves, what are our steps for solving a differential equation using the Laplace transform? So the first thing we're going to do is Laplace transform the differential equation. Then, using algebra, we're going to solve for the Laplace transformed function, capital X of s. Once we have that solution for capital X of s, we're going to use the table, the inverse Laplace transform table, and some shifting theorems. It turns out we're going to need the second shifting theorem here to find the inverse Laplace transform and our solution to the differential equation. Okay, so let's apply each of these steps to the differential equation example we have here. So let's first Laplace transform our differential equation. So when we Laplace transform our differential equation, we have to take a transform of the second derivative. And so using the rules for the Laplace transform of the second derivative, we get s squared times x of s minus x dot at 0 minus s at x of 0. So that's the second derivative term, plus 4 capital X of s is equal to, and now we have to use the Laplace transform of the Heaviside function. And the Laplace transform of the Heaviside function is e to the minus 5s over s. Actually, a lot of these terms vanish because x dot at 0 and x at 0 are both 0. So those terms will vanish entirely. So on the left-hand side, I just have a combination of s squared plus 4 times capital X. And on the right-hand side, I have that e to the minus 5s over s. So there's not a whole lot of algebra actually for us to do to solve for capital X of s. We just need to divide both sides by s squared plus 4 in order to get this second step for the solution for capital X of s. So we're pretty much there actually for solving the differential equation using Laplace transform. The only other thing we need to do is now use the table to find the inverse transform. And the thing that complicates this is that factor of e to the minus 5s. But we know our second shifting theorems, and our second shifting theorem, rather, tells us that when there's an e to the minus 5s, what we should really do is just focus on the Laplace transform of the term without the exponential, so strip the exponential off for a second, find the inverse transform, and then the e to the minus 5s just shifts everything over in time. So, for example, if we strip that e to the minus 5s off, we can find a term in our table that looks like it's going to work. Namely, it looks like we're going to be able to write this in terms of 1 over 4, 1 minus cosine of 2t. But that's not the inverse transform we want. We want to also have the e to the minus 5s in there. And the rule with the e to the minus 5s is that it shifts the time of our function. So instead of cosine of 2t, we have cosine of t minus 5 all times 2. And then we also have a Heaviside function multiplying that solution. So we have u at t minus 5. So that's just using that second shifting theorem here. So this tells us that our solution is this shifted solution, 1/4, 1 minus cosine of 2t minus 5 times u of t minus 5. We just write that on our next page here. And I actually want to break it down into what happens for t less than 5 and what happens for t greater than 5 so that we can try and make sense of what this solution is and to see if it matches maybe what we would have expected. So for t less than 5, the Heaviside function is 0, and so we have 0 times the cosine, the 1 minus cosine term, but then that's just 0. So for actually t less than 5, our solution is exactly 0. For t greater than 5, however, now the Heaviside function turns on and becomes 1, and so we have a time-dependent solution for x of t, the 1/4 1 minus cosine of 2t minus 5. So I've shown a solution here of what that looks like. And so for t less than 5, we indeed have 0. For t greater than 5, now the solution turns on. And the solution that turns on is actually a solution that's just oscillating about the mean of 1/4. And actually, that's exactly what you would have gotten if you had solved the inhomogeneous differential equation, x double dot plus 4x is equal to 1, namely when the Heaviside function is equal to 1, you would have gotten this type of oscillation oscillating about 0.25. And that's exactly what we're seeing here. And so this solution is pasting together the solutions that is 0 for t less than 5, and then the usual solution we would have gotten to the inhomogeneous differential equation for t greater than 5. But of course, we didn't need to know any of that when we solved this using a Laplace transform, because the Laplace transform takes care of everything for us. So that's another way in which the Laplace transform is kind of magic in how it finds solutions for us. Okay, I hope this was a useful example for seeing how to solve differential equations with the Heaviside function involved in them.